Everything okay now for me to make a start? Okay, thank you very much to the South and West Wales PWI section for inviting us tonight to for a discussion about a more modern approach for rail fixings, the Excalibur timber sleeper bolt. First of all, we'll give you a little bit of introduction about Excalibur screw bolts, leading into the product overview of the sleeper bolt, and then focusing on that for the main presentation and technical discussion. Excalibur screw bolts were the original twin helix threaded anchor for all substrates, and our managing director Charles Bickford revolutionised the construction fixing industry with this particular product. It's British designed and manufactured, and we've had the honour of winning 2 Queen's Awards for innovation, one in 2009 and the other one in 2016. The Excalibur screw bolt fixes directly into any pre-drilled hole and gives an immediate high-low capacity. It is a replacement for all types of traditional fixings, including expansion anchors, chemical anchors, large screws, plugs and pins. It can be used in all major building substrates, including concrete, brick, timber and plastic. It has enormous whole life cost and operational benefits for the whole rail industry. We are a proven product used extensively for both temporary and permanent requirements on rail civil and track infrastructure projects. One such project was Crossrail, and the Excalibur Plus bolt was used extensively to fix platform edge screen brackets, GRC panels, cable management systems for a very onerous 120-year design life. Other uses in the railway have included multiple Network Rail and London Underground approvals for the likes of insulator pots for London Underground, stub bolts for high drive signalling systems, and also our 16mm 150 bolts for the Pan 8 base plates, and also a reversion of a 2256 screw bolt with a threaded ferrule for fixing 2-level base plates. This moves us on to our Excalibur timber sleeper bolt. We were approached by Network Rail and London Underground to provide a quicker and easier to install alternative to the AS screw spike, and this was the driver for that fact. So we came up with Network Rail and London Underground engineers a version of our product for this particular application. Loose and missing rail screw spikes in timber sleepers are a commonly acknowledged problem on all rail networks worldwide, as you can see from the photograph in this slide. The issue with the AS screw spikes is it causes splitting timbers at the surface. This is a common degradation for sleepers and bearers using the AS screw spike. Counterboring is no longer carried out at the installation process, and the standard AS screw spike tapered shank sets up surface stress fractures occurring during the installation. As these fractures split, elongate under load, screw spikes lose grip and exasperated by vibration, temperature and moisture. The cracking splitting is more evident within tight curvature, causing excessive lateral loading, increased bending forces within the screw and the fixing hole. We believe a better solution is the Excalibur screw bolt, which is designed with a reduced upper shank height for no counterboring required. The twin helix thread design is much sharper, hence cuts into hard and soft materials, offering much less resistance when threading the form into the timber sleeper. This results in the wood fibres becoming securely wedged between the threads, resisting withdrawal. Excalibur screw bolts require far less force to insert than the AS screw spike. Now we just show you a installation speed test, which we undertook with Network Rail operatives from Eastleigh Depot at Southampton University. Hopefully you'll find this very informative, and then we can start the technical discussion from there. But hopefully you enjoyed the video, and sort of gives a indication of the productivity, reliability, and workforce welfare benefits our product can offer over the traditional AS screw spike. I'd now like to introduce you to Chris Parasam, our development engineer, who will now go through the technical part of the presentation. Thank you very much.
Good evening, everybody. As you have just seen in the previous video, the AS screw spike, it takes a band type machine generating some 1600 to 2000 odd newton meters of driving torque to fit a traditional AS screw spike. That is using no lubricant whatsoever. So into the new hardwood, you've also seen in the previous video the equivalent Excalibur 2163 chair bolt. Now, the picture you are viewing is of a static model that we have. If you look to the AS screw spike, where it's inserted into the top of the timber, you can start to see the initial damage the bolt has caused to it. If you then view on the left the Excalibur screw bolt, you can see the damage is a lot less. So when the ASs start to fail, the damage that you're viewing now on the right will basically form a crater, and the timber will degrade basically, and then eventually the bolt will lose its clamping force. So initially, to get longevity from your asset, if you don't do the damage in the first place, then hopefully the asset will last that much longer. In most of the fitting that you will normally do, because you're putting down the base plate with a ferrule and you're not likely to take it off again, you would never see the damage that's occurred. So a basic overview of the bolt is the Excalibur bolt is a parallel bolt with a raised twin helix thread. So as John said earlier, you have got a bolt that cuts a thread into the timber, as opposed to the AS screw spike, which forces its way into the timber. So as was mentioned earlier, couple of the key points to remember, whichever bolt you're fitting, is if you can try and clear the holes out for sawdust and swarf and stuff like that, any debris. That will obviously aid installation, but with the Excaliburs, there should be no need to ever use any lubricant to be able to fit the bulb. So now you've got the overview of the bolt itself. What we have done with this bolt is moved away from the traditional square head drive to a 30mm AF 6-point hexagon head. Now, the reason we've done this is because in driving the bolts, so much torque is lost from the machine through the method of driving. So when you're driving a square, because it tends to be quite slack on the socket, you're losing quite a bit of driving torque. So that's the reason for putting a hexagon head on it. Also, something else that is worth remembering, the 30mm AF 6-point sockets, if you use the impact sockets, they're readily available from most reasonable tool supply shops. So it's not a special order socket as would be required for the ASs. On the bolt as requirement, the head stamping will always have the year, and it will have the tensile grade, and it will have the length and the manufacturer's name, which is required as a standard anyway. So the bolt you're looking at the moment on the head stamp, it's showing 5.5. So that's the about the equivalent of the standard grade for network rail. Then the high tensile grade becomes 8.8 HT. You drill a 19mm hole as you would for an AS screw spike. So an embedment depth of, if you can get it, about 120mm would be nice. It gives it a little bit of clearance underneath the bottom of the bolt with the hole cleared out, which allows you, if you ever need to do a tighten up, to put the load across the top of the bolt into the ferrule as opposed to the bottom of the bolt into the timber, which consequently gives you your clamping force. So in trials that we did with Southampton, the official testing, the tensile load returned per bolt and the average mean come back at 75.9 kilonewtons. So we have a picture of a piece of track that is some 132 years old, still in service, but it's still fixed down with traditional type fixings. For innovation, railways, infrastructure to move on, the innovation has moved on, basically. So there are newer ways, better ways, hopefully, of achieving what was required as far back as this piece of rail we're looking at 130 odd years ago. Right, now for the more technical side of it. In the picture that you saw of our static display with an AS screw spike and an Excalibur screw bolt into a piece of timber. Now, this is how I can justify the damage the AS screw spike does. If you look at this test is performed between ourselves, Excalibur screw bolts, and Network Rail using Southampton University and obviously their test kit. So what we have in the blue bars on the chart, so to the left-hand side, are tests 1 to 5 of insertion of AS screw spikes. Now, what you're seeing is the level of stress that is caused into the timber, and the average mean on that run out at about 1,050 UE for the AS screw spikes, and the Excaliburs run out at about 220 UE average mean. So what this demonstrates is basically what you will never ever see. This is what is happening inside the piece of timber as you're inserting each of the different types of bolts into it. And again, you wouldn't see the damage at the top because the chair's covering it. So this is part of the reason that you can use battery powered tools, because the stress and strain is so much less for the Excaliburs, which are the orange bars on the chart. The allowance is that you need a less powerful tool. So with the Excaliburs, they're going to fit at somewhere around 250 Newton meters of torque, as opposed to the ASs, which are going to require somewhere between 1,600 and 2,000 Newton meters, which would be used from or produced from a bounce type machine. So if we move on to the next slide, this series of slides is the strain gauges which are placed around the holes. So I need to just refer to my notes for this. What we have is strain gauges 1 and 4 are closest to the hole. So 1 and 4, and I can't read that. The coloured lines. So on the left-hand picture, that relates to the fitting of AS3. So these installations were done partly for the testing of the tensile loading of the bolts. So if we, first of all, we look at the left-hand graph, what we can see is this is strain over time. So the installation time was nearly up to 30 seconds, and the strain on the worst gauge, which is furthest away, I believe, strain gauge 1, right? So right, strain gauge 1, sorry, is the closest to the hole. So what this represents, what this represents is the amount of strain that is pushed back into the timber. As you can see, it is somewhere in the region of minus 1500. And if you also look at the time duration, this doesn't drop back either. So this stress and strain is retained within the timber until either the timber starts to split, which is probably what is going to happen in the case of this one. Whereas the other strain gauges that have moved further away from the hole, the strain is significant, and also the strain doesn't dissipate when a period of time passes. So now compare this to the gauge on the right-hand side, and this is the representation for Excalibur bolt 3, number 3. So the installation time is about 8 seconds is taken. The highest peak of stress this has caused is just about 210, 220, minus 210, minus 220. But what you will note from this is that the stress dissipates. So the red line on the right-hand graph, although it raises up, it is nowhere near to the equivalent of the AS screw spike. But what you will also notice is that the strain drops right the way back into the timber. So the strain that is left in the timber basically is probably, without having the actual figures to hand, only something like 30, as opposed to, obviously, when it's fitted, the highest strain closest to the hole become minus about 210, 220 for the Excalibur, but for the AS, it's gone up to the best part of 1500 on the minus. So that's part of the justification for being able to fit the bolts that much faster, and obviously it's reliable fixing, doing a lot less damage. So we'll move on to the next. Right. These charts that we're looking at now, this basically is the test again, that is one of the tests again that is performed in conjunction with Network Rail Excalibur screw bolts at Southampton University. This is all official data as well that you can access if it's of interest to you. So what we're looking at now is an assembly stiffness test, but the assembly consists of a short piece of rail about 250 millimeters long, a pad that it sits in, a PAN 11 base plate, and then 3 chair bolts, either AS or Excaliburs. Both were tested in several sets of tests. So if we look at the first graph on the left-hand side of the page, what you will see, this represents the amount of cycles that the assembly, in other words, the bolts, were subject to. So you've got the amount of cycles that run along the bottom, and then a measurement of how much the bolt winds out basically is to the left-hand side column. So what you'll see is in blue represents the AS screw spike. In orange, it represents the Excalibur chair bolts. So for the first part of this, at 600,000 cycles, 105 kilonewtons of vertical load onto the rail. Incidentally, to induce failure, what had to be done was the PAN 11 base plates have I believe it's a 3-degree incline for the rail. So what had to be done was it had to be turned the opposite way to use the 3 degrees against the load force, so to induce. So in other words, what I'm basically saying is the load was put onto the single bolt side, and it was arranged in a jigged frame to be able to adjust the angle to increase the amount of load that was applied to the side of the rail. So I slightly diversify there, but we go back to 600,000 odd cycles at 105 kilonewtons. Now, the AS screw spike at that point, it starts to unscrew, and it lifts by some 45 odd microns. Now, microns doesn't sound a lot, does it? But this is representative. So we move on. It's done 1.2 million cycles, and the load, vertical load, has been increased to 120 kilonewtons. Now, at this point, the AS screw spike has now moved out by somewhere approaching 70 microns. So that is the blue bar representation. Now, if you look at the orange bar, which has the Excalibur screw bolt has run through the same cycle tests, where it is in relation. Now, that is 10, maybe 15 microns at the most, at 1.2 million cycles with 120 kilonewtons of load on the top of the rail. Now, if I remember rightly, the maximum loading that was supposed to be applied to the top of the rail was 120 kilonewtons, but obviously we wanted to find out the exact point that this would go to. So the loading carries on. It's had its running period, 600,000 cycles. It's now been loaded to 1.2 million cycles at 120 kilonewtons. It does a further 1.8 million cycles at 130 kilonewtons of vertical load. And again, you can see obviously the results, the blue bar representing the AS, the orange bar representing the Excalibur. We go on into the next set of cycles, 2.4 million cycles, 140 kilonewtons. And basically, if you follow this through, 3 million cycles at 150 kilonewtons, which is possibly 30 kilonewtons overloaded on the top rail at that point. So what is happening is the AS screw spike is basically unscrewing. As you see the blue bars rising, that's what that represents. So 3 million cycles at 150 kilonewtons. By then, the bolt, the AS screw spike is unscrewed by somewhere near 110 odd microns. The Excalibur, on the other hand, is somewhere around 18 microns. So the representation is there in the different rates that the bolts do come unscrewed. So that's one set of testing and one set of findings. If you now look at the right-hand graph, what you'll see is this time there was a small running period of 900,000 cycles at 100 kilonewtons. This basically is done for a bedding to bed all the components together, any linkage that might be required into the timber or whatever needs to happen, it settles it down. So what happens here, at 100 kilonewtons on the vertical load on the top rail, the Excalibur starts to unwind out and it gets to somewhere around 55 microns. Right. Now, this test, what is different between the two tests that you're looking at is this test is then loaded to the maximum after the running in period. So it doesn't gradually increase in load. This is just full on load. So we have 1.2 million cycles, 150 kilonewtons. Now, at that point, what we know in this particular graph is that the AS screw spike has started to come undone. It's lifted by approximately 20 microns. So we can then ask the question, why is there not an orange bar alongside this? But the answer to this is what the bolt has appeared to do is it's gone back to 0, which is the set point. So by set point, this is where the bolt would have been tightened up to prior to the test starting. And then obviously the gauges are put on to measure the amount of movement the bolt lifts, and also the loading on the machine is calibrated and gauged. So this begs the question then, we go on to 1.8 million cycles at 150 kilonewtons vertical onto the top of the rail, and the Excalibur slightly starts to come undone a little bit. We've got probably 5 microns at the most. So what we need to remember at this point is the Excalibur, it started off on a low load and it come undone. It then, on a full load, has gone back to its original set point. It has then come slightly loose again, but nowhere near compared to the AS. The AS screw spike at this point, where the Excalibur is maybe about 5 microns, it's lifted up. The AS screw spike is approaching 40 microns. So again, microns, it's nothing. You know, it's a measurement you wouldn't even see, but it is representative. So we now look at the point we've got to 3 million cycles at 150 kilonewtons of vertical load. Now, what's happening here? Right, well, the answer to this is the blue bar, the AS screw spike. It has lifted by something like 115 microns. Now, when you look at the orange bar, which represents the Excalibur screw bolts, what has happened? You've got your zero set point, which is the representation of above and below and in the graph. Now, the Excalibur, basically, it has gone back to its set point and then it's tightened up another 20 to 25 microns. So this begs the question, could this, under high load, heavy duty use, could this be a fit and forget bolt? I'll leave you to think about that one. So, here we have a view. Figure 19 is of an AS screw spike screwed into the hardwood timber. This again is official testing between Excalibur and Network Rail with Southampton University performing the tests. So figure 19 is a static tensile load test. Now, the load cell will pull 4 millimeters distance per minute. So in the picture that we can see, figure 19, which is the left-hand picture, you see the destruction that the AS screw spike causes. See the size of the timber in the hole it's breaking out. Right. What you can also see in this picture is you'll see some cables with a lot of wires running into what looks like well, it is basically, they're the sensors that are measuring what's happening within the timber itself. So if we look at the size of the breakout of this piece of timber, it is huge for the AS screw spike. If we now look at figure 21 for the Excalibur screw bolt, the breakout is a lot smaller for this. So again, you can see the sensors, you can see the cabling, and you can see the sensors where they're attached to the timber to obviously record what is happening within the timber, the stresses and the strains. Now, these would have been the samples, the strain stress test, would have been conducted on. 5 samples were required of each product, the AS screw spike and the Excalibur screw bolts, to perform the tests for the static tensile load tests, and then the figure is deduced from the average mean from that. So we're now looking, figure 24 is the test samples that were done at Southampton University. Again, Network Rail and Excalibur screw bolts. So these holes, these pictures are pictures of holes that have been through fatigue testing. So the fatigue testing is the cyclic testing that we've previously looked at in earlier graphs. So you can see Excalibur sample 1, pictures 3 and 2. You can see that basically there is no damage to the timber. What it is worth looking at as well is in this, there are very few cracks across the surface to the top of the hole. So this was sample 1 that was taken for the example. The next photograph, which is close up of Excalibur sample 1, again, you can see that the bolt screwed in and there's a black pen mark round the hole. This represents where the bolt seals into the top of the timber. So the shank just starts to sit into the top of the timber. This is done to reduce the chance of water ingress into the timber. Again, note that there is very little cracking around the surface on the timber around the hole. Now, go on to the next picture, which is AS spike sample 1, picture 1. If we look at this, what we can see is the damage that's been done where, had the hole have had a counterbore in it, it might have reduced the amount of damage it did to it. But when we look at the surface, the splitting to the surface is a lot more apparent. So again, in the earlier graphs and that we've shown you, you can now start to see the representation of how destructive the AS screw spike is. Again, in the last set of pictures that you've got, AS spike sample 1, picture 2 and picture 3, to look at the surface of the timber, and you've got quite heavy splits virtually across the centre line of the hole. So again, this is representative of the amount of stress and strain that's being put into the timber. Right, so now we go on to obviously the cost-benefit analysis, coach group comparison chart. Now, how do you justify this? Well, it might be better for me to let John justify this because it's more his department than mine. But what we'll do is we'll go through this. So the criteria is tensile loading. What do we see? Importance rating, right? The importance rating is 0.15. So option 1, the AS screw spike. Now that's got a plus because it's in the green of 0.15, and the Excalibur has a minus because that is in the red of 0.15. So what is representative of that is will pull a slightly higher tensile load, but for the requirements of network rail, it isn't required to obviously draw that sort of higher load. The downside is the damage that it causes to your assets. Again, this is all within official reports. So if we move on then to overall screw performance, again, the difference is 0.15. So now in this, the AS screw spike loses out. It's minus 0.15. The Excalibur will be plus 0.15. So Excalibur has a better overall performance due to its thread cutting design and reduces stress in the timber. So you've got that as an advantage straight away. If we move on to life cycle costing, this is rated at 0.2. So the AS screw spike is on a minus in the red of 0.02. The Excalibur is in the green, so that will be plus 0.02. Excalibur bolt improves life cycle costs and reduces damage during installation, which we've demonstrated through the various pieces you have already seen. So we then move on to cost per unit. Now, cost per unit is 0.2. So the AS screw spike is on a plus because it's in the green at 0.2. The Excalibur is on a minus in the red at 0.2 because Excalibur screw bolts are produced in the UK, in the Midlands. They are completely made, manufactured, finished in this country, heat treated, plated, all the processes it needs to go through. So that thus provides income, employment, skills within the UK. It keeps the money moving around for the UK economy. So none of this is imported from abroad. It is all UK manufactured. So unfortunately for us, because we are doing this and we are not looking to China, India, Turkey, Poland, wherever, we do have to pay a slightly higher price as we have slightly different overheads and minimum wage and everything else within this country. Now, we move on to going green. So sustainably, CO2 emissions. Again, this is rated 0.1. So the standard AS screw spikes is on a minus 0.1 in the red. Excalibur is on a plus in the green. So installation for Excalibur using battery powered plant produces less emissions as opposed to using a two-stroke petrol powered BAMS type machine. But also it is worth thinking about as well within this, because we're in a changing planet where now we're talking about our carbon footprints. What I basically just said to you about this is produced in the UK, it is a reduction in carbon footprint for the manufacturing and the movement of the product because it is made in the UK, it is used in the UK. So that is worth considering. We move on to Operatives Well-Being. Again, this is rated 0.1. Now, the AS screw spike, as you have seen through the installation video, it's on a minus 0.1. Excalibur is on a plus 0.1. Lighter tools, reduced duration of exposure to halves, is the reason that has been given to that. So we move on. Ease and speed of installation, again, 0.1 is the rating. So the AS screw spike, unfortunately, has a minus 0.1 and Excalibur has a plus 0.1. Excalibur, because it is that much less stressful, let's say, is 4 times faster to install than an AS screw spike. And also, it's worth remembering that you don't need oil, you don't need grease, and other methods that may be incorporated to fit a stubborn AS. So that is worth remembering. So the total of importance rating is 1. For the AS screw spike, it is given a minus 0.3 out of 1. For the Excalibur, it is given a plus 0.3. So if we sum this up in total, the sum of pluses for the AS screw spike, you've got 2 pluses against 4 minuses. For the Excalibur screw bolt, you have got 4 pluses against 2 minuses. So that may help you in the cost justification. We hope it does, and obviously any questions, please feel free to ask them. So the summary, basically, to sum up on this, Excaliburs are 4 times faster to install, take 5 times less effort. They're a patented, unique thread, which, as was explained to you earlier, come from a completely different world, let's say. They're a robust bolt, which is pretty much vibration resistant. So you've got improved safety and reliability from that. And do load situation, what we saw in the second bar chart where the cyclic loading was being done. For any engineers out there, it is very hard to believe but that is the case. But that is officially what was recorded and come back from the official testing. So, benefits. Workforce welfare, including reduced hand-arm vibration, COSH, manual handling, and workforce fatigue. So you can basically get more done in less time if you want to. And not have your arms tingling and your fingers and your wrists about to pop out their sockets. So it's a UK designed, manufactured product. It goes through product control, quality assurance, environmental impact and sustainability are obviously a lot better because it is a UK manufactured product. Network rail and LUL whole life costing benefit analysis, which you've just seen in the matrix previous to this slide. Both network rail SME action plan and combination with the government's rail sector deal is committed to developing a safe and substantial UK rail sector at home and abroad by encouraging innovation, supporting British SMEs, growth throughout collaboration and implementation, intelligent procurement processes which value the whole life costings. So for future references, the documents I have referred to, the reference, you can obviously see this on the screen. Southampton University is Dr. J. Thatcher. That relates to the graphs and the technical aspect of it. We have a network rail ergonomics report, which was done by E. DeMello, and I believe the number of the document is there for any of those that can access the network rail documents. And other references are to Dr. Poparola, Imperial College, London, for testing of Excalibur plus bolts that were used in the Crossrail project that is now coming to completion. If anyone has any questions, I may be able to answer them for you.
Right. Thanks very much, guys. It's very interesting. I'll start the questioning off, if I may. My question is about corrosion protection. The AS screws are traditionally galvanized, aren't they, as protection? What anti-corrosion protection do you put on your screws?
Yeah, we were asked to put standard zinc plating on the original specification, but a lot of our products now are mechanically zinc plated,
Right.
which gives 1,000-hour salt spray resistance. So it's a not like galvanized. Obviously, is quite a environmentally harsh product. You know, it's molten zinc. So. So for our standard product for concrete screws, because we've gone to a mechanical zinc finish, which we've tested to 1,000-hour salt spray resistance, it's literally applied by beads being pummeled into the product, and with a high quality basically sealer onto the product. So that satisfied from Crossrail for their 50-year design life. So that's what we've gone to, and that's what we would like to move forward to with the rail industry, to be quite honest. So but the initial spec when we first looked at this was a number of years ago now, and that was just a zinc plating finish.
Yeah. Okay, thank you. Right. Any other questions? Got no more coming, so I've got another one for you as well. So, I've got a hand up. Let's see who's here. Right, Stuart Lizelle, can you? Oh, Stuart.
Hello, everyone. Yeah, my question is going to be: we've spoken quite a lot about sort of timber sleepers, but obviously with in Network Rail, we obviously now can't use them anymore as we move forward to plastic sleepers. How do you guys cope with those?
Effectively, the same thing happens in plastic, because basically a plastic You know, the AS screw spike fixes in the same method as it does into timber. So it grabs a great big hole at the top of the hole and forces a bit of plastic out the top of the hole. We have examples of that where we've done similar testing install. So you are effectively damaging your asset with a screw, whether that be plastic or whether it be timber. So there is those benefits to our product. Chris can probably elaborate more on that.
We have this is more difficult to sort of explain because we have static models that we produced. What has been noted with the side cut type composite sleepers, the black plastic, is that after a period of time, when you do close edge fitting, the plastic starts to split. Now, I know you're going to say to me, well, we wouldn't fit close to the edge, but these are simulations that if we were all together now, we would show you the physical models and be able to demonstrate the damage that's caused. So on London Underground, they are using composite sleepers, which they are using Excalibur screw bolts, the same chair bolts as you would have, but theirs are 8.8, so that would be the network rail high tensile equivalent. We have done testing in a fiberglass partner for Secretary, but unfortunately, the bolts you're looking at the moment, the official testing is for timber. So moving on, there may be a possibility in the future that we do more testing to allow it to be used into composite type sleepers. But for your information, I did some work earlier this year and late last year for Pandrol in making them a special bolt to work with a new type of chair into a composite sleeper, but at the moment that is still sort of work in progress. So we realise that the future will go that way, but for the moment you're stuck with that for timber. So
yeah, we understand obviously the benefits of looking for you know recycled plastics, etc. in the round, and we totally get that argument, but obviously in the meantime you've got lots and lots of timber out there through which basically you're using a very harsh and destructive product which takes a huge amount of effort to install, which won't be, you can't use battery powered equipment to install it because it just takes so much effort to it all. And as you know, we've in the past, you know, you're trying to protect your workforce and make their lives easier, make your whole life more productivity, you know, reliability and benefits. So it's what, you know, there is now an alternative to what you've always used, basically, which is much quicker and easier to use and has a cost benefits, whole life cost benefits to it. So there is, you know, so there was no other way, I suppose, you know, many years ago, that was your only option to have. But now there is another option, basically, to make it, say, we've done a lot of testing, well, I say trials now with Wales and Western Route, and, you know, the time savings are there to be seen, you know, the hours saved, overall productivity, you know, man hours on plant, etc., you know, are quite considerable. So it is really a case of, you say, or Network Rail, London Underground, they all say we want to protect our workforce, we want to do things quicker and easier, more productive. Now there is an option to do that with your fixing and not stay in the Victorian world, which has a fixing that requires an enormous amount of torque to install and can only really be installed properly with heavy industrial equipment, basically like the Vance type of machine. if you were to find some form of battery equipment that will do the job, you know, again, that battery is being exposed to 4 times more effort than it would do with an Excalibur. So it's, you know, hopefully we're getting the word out there to people, and you know, we've done all the technical assessment of the product, you know, and the products, we've got a proven product that's been used extensively in the rail industry for many, many years now. So we're hoping that people, you know, that video in particular, you know, is showing people exactly what the product can do for you.
Okay, thank you, guys. Thank you, Stuart. Right, have we any more questions? I'd like to ask another question about the tightening effect, or the apparent tightening effect. I was noticing on your graph that the implication is that the Excalibur bolt actually tightens itself up. Do you understand what's happening, or is that something that's going to carry on? I mean, are you going to start overloading the bolt because it keeps getting tighter, or is that more research? I don't know.
I think that's wishful thinking of overloading the bolt, to be honest.
Yeah.
What I can tell you is we have seen our bolt originally was a concrete anchor.
Yeah.
And still is produced as a concrete anchor. Now, in some of the testing, which you can reference, I think, on the Imperial College document, what you'll see is when the product was cyclic loaded, but this is referring to concrete, it was found that the tensile loads would increase on it, which doesn't exactly suggest that it's tightening up, but it doesn't say that it's coming undone. So I've been an engineer for 40 years now, and I've spent most of my life finding ways and methods to stop things flying apart.
Yes.
For want of a better word. So when I saw this, you know, I'm very sceptical, like you obviously are, over stuff like that when you see it, because it's not the norm. It's not what happens. Normally, something that's subjected to sine wave, you know, vibration and stuff like that, normally it ends up coming apart.
Yeah.
So in this particular scenario, because it's overloaded, basically, so it's the simulation of running high, heavy loads. That's what's seen in effect, but it is, you've got to remember, it is overloaded. So if I can remember this rightly, in, say, engineering trains, they can go up to something like 500 odd kilonewton axle loads. If I'm correct, I mean, I'm not
on network, right? Not on network rail, but
yeah, forgive us. We're not a rail.
Yeah,
we're not a rail specialist. We've got a lot of rail products used on the railway and rail products approvals, but effectively we were a construction fixings company that's moved into the rail.
Yeah. So what you're saying is, under normal loading, then basically what it's demonstrating is it's not going to work loose. It's the key thing, isn't it?
Yeah. You've hit the nail on the head there, Andy. Basically, we have no history of our product coming undone, whereas obviously the AS screw spike has a massive history of it coming loose.
Yeah, and indeed breaking. Yeah. So okay, but Andrew Wilson's got a question. Andrew, do you want to come on and pose your question? Yeah.
If I can unmute myself and even turn my camera on.
Yes.
Yep, maybe.
Yeah, got you.
Can I just go back a bit and investigate what used to happen to the dear old AS chair screw? And sorry, I'm a bit long in the tooth. And the experience of the AS chair screw was that it was not really used much on the old Western region until after I joined, or just before I joined in the late 60s, 70s, and 80s. Before then, the Western had always used a through bolt.
Yeah.
And one of the things that happened with the AS chair screw was it was installed in concrete sleepers.
Yeah.
With a rubber ferrule cast into the concrete, and then the AS gone into screwed into that. And the failure mode of the AS concrete sleeper was that under fatigue loading it would fail in shear, particularly on a canted curve. And I just wonder, we've also had the recent derailment at Eastleigh, where the derailment occurred on a similar long-ended pandrol housings, again into concrete, where they failed in shear, quite deep down in the concrete, say 25 mil or so, and very difficult to detect until it actually falls out or sufficient fail to cause the derailment. So can I just say, have any tests been carried out on the Excalibur screw bolt in pure shear for very repeated loadings over simulated many years?
Well, the cyclic loading you saw in the Southampton test reports is basically to try and, as best as possible, reproduce sort of the dynamic wheel loadings that would be applied. So if you remember, or if you were present at the time, what happened is on a Pan 11 base plate, you've got two bolts one side and you've got one bolt on the opposing side. So that base plate, if I remember rightly, it's got a 3-degree cant to it. So what it's doing is trying to push the loading onto the two bolts, if I'm correct.
Mm-hmm.
So because obviously in a lab test, to induce failure, if you're trying to make two bolts fail, it's going to be more difficult than making one bolt fail. So what they did basically was reversed it around and then in a jig tipped the base plate over and then kept adding more degrees to it to make the lateral loading increase up to a load of something like 30 odd kilonewtons. So it goes, in the testing, it goes from sort of 0 or 5 kilonewtons up to a maximum lateral of about 30. On the vertical, the overhead, it runs from something like 100 kilonewtons up to about 150 kilonewtons. But if I remember correctly, in the actual testing schedule under the relevant standard that's required for it, the loading, the vertical loading, doesn't need to exceed 120 kilonewtons, but you would still run between, say, 0 and 30 degrees laterally on that. So at the end of the day, as far as the shearing goes, it wasn't possible in testing to shear any of the bolts under that test regime. So a question I would ask about, obviously, what happened at Eastleigh is, if the bolts come loose and they're starting to move about, then obviously if the whole assembly it's lost its stiffness, would that have been the scenario, do you think, as to the bolts breaking there? So in other words, the bolts start to come loose, because the AS is a tapered sort of bolt, effectively it's lost any clamping force it would have had by the time it's lifted less than an inch. So effectively, I can't remember what the thread pitch is at, but I think it's about ½ inch. So effectively, it's probably lost anything more than being a bar once it's lifted by about ½ inch. Would that have been the scenario that happened there, do you think? Or
I can't remember the full.
Eastleigh was was a pandrol fastening, but it was the shank of the housing that broke off due to overloading, I think, because the shank wasn't increased in size when they increased the moment on it. The Sheffield derailment we had recently was the scenario of the coach screws breaking off at the basically where the taper finishes and the thread starts. They broke off there, but again, it's because they had worked loose. Yeah, so that's,
yeah. Well, that's all
the problem is there's no obvious sign of them having worked loose. They weren't sticking up and they felt tight. That's the challenge, I think, is how do you test these things? So.
Well, at the end of the day, you're using traditionally a product that it's hard to fit in the first place. So, you know, this is no criticism, obviously, to the permanent way guys out there battling in all weathers trying to fit this stuff and that. It's no criticism whatsoever. But I've been out recently on a bridge renewal where the timbers were renewed on a bridge, and the guys did a shift change, and the day crew basically they got on pretty well, but they struggled with their bounce type drilling machine. They struggled to put the holes, you know, centre the holes up properly. Part of the reason for that was because the base plates they were working with had the pandroll clips and that on them, and then they were screwed down. But what they ended up having to do was take the centre guide, which fits into the ferrule, to obviously centre the drilled hole within the ferrule in the chair. They had to take all that away. That then gave them a bit more access to be able to get the machines in to drill the holes to the depths they needed to, but they still struggled because the drilling machines still had the depth gauge legs on them, so they struggled basically with their equipment, and it was maybe fortunate that we were there, and we work in a slightly different method where we use bosses or drill jigs, if you want to call them that, to centre up properly, and the depth gauge is a boss that is attached to the drill bit itself, so we set the depth and then we go in and just drill the hole. So we haven't got all the cumbersome components that the bounce type drilling machine has around it, and that's only one of my observations. So coming back to the relationship of shearing, once the clamping force has been lost, in the lateral load, it's going to put everything into shear. Yeah. So if the longer you can keep the clamping force in situ, then the better it is for the stiffness and all the components that are working with it. Because you've got basically plastic nylon type ferrules, which I've seen them split in the past. You know, once the ferrule has gone, and if you end up with metal to metal contact, then obviously that's even worse. There's nothing there for a cushion to try and absorb any shock that is lateral. So again, it returns back to if you can keep the clamping force for longer, that way you should have a lot less issues as far as shearing goes.
Yeah. So coming back to your point, Andrew, the Great Western's fastening system with the through bolt is actually a much more efficient fastening system. So in that it doesn't use it uses an engineered bolt, and the shear resistance is actually maintained by the fact that the bottom of the base plate is serrated and engages with the timber. So it's not relying on just the bolts should never come under shear. So right. Okay, any more questions? Right. Well, there's no more questions come in now from any of our other speakers. So if there's no further questions, I'd like to Thank our speakers very much again for a very interesting talk, and I think I look forward to seeing you in Bristol if you come over in November and actually having a look at some of your products on the table, as it were. So thank you very much for a really interesting talk. And I think there's certainly a lot to take away and think about in this. And like a lot of these things, we in the industry, we're quite a traditional industry and we use what we used to. But clearly, we're having lots of failures of the AS and indeed the Voslo screws. So perhaps it is time to have a re-look at something, a new engineered product that can solve some of those problems for us. Okay.
Thank you, Andy. Yeah, we just say thank you very much for the opportunity of showing our products benefits, we believe, which hopefully you've seen that, and we believe you've got something that's of benefit for the rail industry, and will help improve the fixing reliability and the workforce welfare, and also maintain your asset for longer. So we hope that we are, as you say, you're a traditional industry. You take a lot of convincing to move over, but as I say, we've had a lot of our product used now for Pan 8 base plates. We're now getting quite a lot for the traditional chair screw as well. So hopefully we can work hard with you guys to convince you to try us, and hopefully you'll see the benefits once you do.
Right. Okay. Thank you very much. So could those on who've unmute yourselves and show your appreciation in the usual way. So. Right. Thanks very much indeed, guys. All right. Thank you.
Bye-bye.
Yeah.
Bye.
We've got some virtual clapping going on as well. So. Okay. All right. Thank you.
Thanks for the opportunity.
No, not at all. Thank you.